First in this talk, I'm going to give you a little bit of biology. I apologize, but it is necessary. And I'm going to talk about origami viruses. By the way, this thing in the top right is a virus. It kills little babies. And that is a little origami model of it. And I'm going to talk about, and end by talking about crafts in general, like origami and computer models. And it's all about education. I mean, that's sort of obvious. We're here, right? Okay, so first the biology, and I'm just going to switch to this thing. What you're looking at here, as I said, is a virus, and I'll just rotate it so you can see it a little bit better. It's all yellow, so let's add some color to it. The virus, these colors are not real. I just picked them randomly so that you can see that it's made out of identical pieces, right? It's pretty important. Viruses are made out of identical pieces. This is a virus that causes pneumonia, by the way. Okay. Why do viruses harm us? Well, first we need to know how they reproduce. First, a virus needs a cell. This is a cell. A cell is much larger than a virus. A virus is not a cell. They're quite different things. And I'm just going to simplify and say that the cell sort of mistakes the virus for a piece of food or something else that it needs, and the virus gets inside. And after that, you get inside of the cell, the machinery of the cell that's meant to reproduce the cell. It thinks that the virus is a part of it. So it starts reproducing bits of the virus. Okay? This is a cell under a microscope that is reproducing parts of that virus. In particular, it's reproducing these segments of it one at a time. The identical pieces are being reproduced. That's the thing that's highlighted in pink. Eventually, you have a cell that is full of viruses. Very nasty. And then the cell bursts because it's full of viruses, and those viruses go on to infect other cells. And this is what kills us, right? This is HIV. This is Ebola, etc. What I want us to think about in this talk, though, is the part between this and this. Because in this picture, you've only got bits of the virus. You haven't got the full virus assembled like this. So how do we go from little pieces of a virus to a full virus? Okay.
A virus.
So what we have in this video is a little toy that someone has made where they've got little plastic pieces. They're all the same. They are in the same sort of shape as virus pieces. And they've got little magnets on them as well. So if two of these little plastic pieces in this jar here collide with one another, they fuse together. Now inside of the cell, things are very chaotic, so they get shaken around like this. You can start to see something taking shape. So you can ask the question, why do viruses look like this? And I brought it to a maths conference here because it looks quite mathematical in a sense. Some of you might have recognized the symmetry on it already. Now here's a little quiz question for you. I've got two things that are made out of 6 pieces. I've got a cube, and obviously a cube has 6 faces. We've already heard that. And this is a sort of coffee machine thing that's made out of 6 pieces. Now I want you to imagine that I put all of these pieces separately in jars, and I start shaking those jars. And they've both got magnets attached to them. So it's just like the thing that you just saw. Eventually, they'll both assemble because the magnets make it sort of inevitable. But which one of them is going to assemble first? The left-hand one, the cube. Why do we think that the cube is going to assemble first?
Because it's got more possibilities.
Because it's got is an excellent answer. There are other answers that I would accept. And I just want to say that I've shown this to 13-year-olds, and that's a pretty good piece of education in my opinion. Because you don't usually get to use your head very much in biology, to be honest. I'm sorry. I'm doing a PhD in biology and it's like that sometimes. Well, at least at school level, blah, blah, blah. Okay. Yeah. Okay, so just so we're clear on this, there are other virus patterns that you get. They're quite pretty, in my opinion. Forget what that one is. That one's Zika virus. This is a virus that causes cancer. But, as mathematicians, these sort of appeal to us. And by the way, any of you who have seen the work of Brian E. Thomas before might have seen these patterns before. But okay, we are interested here in origami viruses. So let's see some of them. Here's the virus from the beginning, and apart from the combination of the colors, these are the same shape. And I promise, if you were to stare at these for the longer you stare at them, the more you realize they have in common. Here's another example. This is rotavirus, and here's a model with a very, very, very similar pattern. Well, identical pattern. One more example. This virus affects cats. The colors, again, are artificial. I put those in. But one thing I want to say about this origami model, and all of these origami models, is that they were made by people who had never seen a virus. Now, why would an origamist accidentally make something like a virus? Here's another example. It's maybe harder to see the correspondence in this one, but trust me, the pieces of origami assembled into that model there are assembled in exactly the same way that the molecules are put together in that virus, which affects potatoes. Okay, why have origamists unconsciously imitated viruses? Well, number one, both of them need stability, and so they make spheres. If you're an origamist, you don't want your origami to fall apart. If you're a virus, you don't want to fall apart until you're inside the cell, but blah, blah, blah. Both need stability, so they're made out of spheres. That doesn't get you all of the way towards them having so much in common because, well, those aren't spheres, by the way. Topologically, they're spheres. Balls of yarn are spheres, but they aren't very much like viruses. But okay, here's point number two. Both of them want less to remember. Now, what do I mean by that? Well, if you're an origamist, you want to have fewer instructions because it's easier to remember. That just feels a little bit nicer. And so it's a quite good strategy to make a nice big model out of one piece. The one piece only has a few instructions, and you get something that looks complicated, right? Similarly, if you're a virus, you actually want to have you want to be made out of as few pieces as possible, because the more different pieces of you there are, the more DNA you need. That sounds a very sort of abstract connection there, but it's true. We have lots of DNA. Viruses have much less DNA than we do. And finally, they both need to be self-assembling. You can see why a virus needs to be self-assembling. I showed you that shaking thing, but yeah, a virus needs to be self-assembling because there's no one that's going to come along and put it together. If you're an origamist and you're writing a book and you're making a model that you want to be created by a little kid, kids, they do their best, but often they're muddling along. So you want them to get to the answer as quickly as possible. So essentially, you want self-assembly for the same sort of reason. Okay. You have the same mathematical specification, so you get the same patterns. Kind of interesting, and for me, a bit deep. That's kind of what made me want to study mathematics when I was in school. And here's just a bit of a curiosity. Here's a partly finished origami virus that I was making. You can see the finished version in the exhibition hall. If you are making a piece of origami like this and you go a bit wrong, you start making the wrong pattern, it can sort of force you to continue making the same pattern. So this is, in some sense, this gone wrong. It obviously still looks very nice, but if you accidentally put a hexagon instead of a pentagon, then you end up repeating hexagons. And the exact same thing happens with viruses, which I find amazing. And in fact, there are possible future medical treatments that are based on trying to make viruses accidentally create weird things like that. That long tube thing is meant to have become a virus. Okay, curiosity number two. There was a guy who was trying to make an origami Penrose tiling. Probably a lot of you will know what those are. It's okay if you don't, but he wanted to make an origami Penrose tiling, which is a great big flat pattern. But he found that it was the paper sort of wanted to curve around. So he was like, okay, why fight it? I'll make a sphere. So he made a Penrose tiled sphere. It so happens that there are virus models based on Penrose tiled spheres. And it took 20, 30 years for this model to be created by a woman here at York called Ryden Tavarrok, who also inspired me to go into biology. And this guy accidentally made something with a close correspondence to this, and he made something with an exact correspondence to it later on. So I find that kind of nice. Here's a little lesson plan for you, if there's any secondary school teachers or whatever in the audience. This is a unit that you can assemble into a little virus like this. This unit is very easy. It's only 45-degree angles and 90-degree angles, so you don't really get origami that's much easier than that. So yeah, oh, and you need 30 of these to make one of those. 30 is approximately the number of kids in a class, right? So yeah, if you're unlucky, obviously. Okay, final part, crafts, computers, and education. Okay, another little analogy from mathematical biology. Maybe some of you know where I'm going with this. There's a nice piece of coral, okay? And here is a knitted, well, a bit of crochet. And it's gone wrong. That's not the way that you're exactly supposed to do crochet, but a lot of people who do crochet will accidentally make one of these. And this is another example where superficially they look similar, and if you continue looking at them, they still look similar because they're mathematically very much the same. And there is a woman called Margaret Wertheim who has a wonderful TED talk on that. Another example, in mathematical biology, a very important thing is protein folding. Some of you might have heard of that. Protein folding often gets compared to origami, which is a bad idea. It's nothing like origami, but it is a little bit like balloon twisting. Yeah, you start out with a long string of molecules, and it folds up into a three-dimensional structure, very much like balloon folding. You even get little angles that are quite similar to one another. Paperclip folding is another thing that it's quite like. Paperclip folding is nothing like paper folding. It's horrible. It destroys your fingers. I don't recommend that you ever do it with children, but that's kind of interesting, right? Finally, basic symmetry. Symmetry is a very important way to classify animals. Yeah, it just is. Radial symmetry, bilateral symmetry. Snakes have translational symmetry here, and you probably know what I'm about to say. Paper cutting. We all like paper cutting. Yeah. Crafts make a lot of analogies. It's almost suspicious. It's not completely crazy, but yeah, I think this requires a bit of explanation. There's lots of great analogies that you get from different crafts. As I see it, a craft takes a simple material, like a string, paper, etc., and it defines a method of manipulation. It's like you're not allowed to cut the paper, or you are allowed to fold the paper. It defines rules. And it seems to me that that's a bit like manipulating mathematical objects according to axioms. What do humans do with crafts? Well, we push the crafts to their logical limits in order to surprise our audience. We want to make people say, wow, that's made with one piece of paper? That's what you always want to hear as an origamist. And that's a little bit like mathematics too. I'm not saying that it's exactly the same, but yeah. Also, crafts are all qualitatively different from one another, right? They just are, and so that means that there's a great big space of different phenomena in crafting that you can see all the phenomena, and you can say, oh, here's something that I like and I can use as an analogy. My favorite of all of these is paper snowflakes. You're a kid and you cut up some random paper and you unfold it, and you're surprised by the result. You go, I made that? Wow, how does that work? And so you maybe make another one and you experiment and you start using your head like, oh, I can make a straight line through the fold if I cut perpendicularly to the fold. And then you get better at it and you feel good about yourself, etc. This is all what Albrecht was saying, which is very, yeah, I strongly agree with everything he says. The kids teachers themselves. Origami, I like origami, but this is something that paper snowflakes have over on origami. In origami, you're doing what you're being instructed, which is not so good. You use your hands in paper snowflake making, and your hands are just so good to do things with. You use your eyes. You don't need to imagine the maths. You don't need to imagine some abstract thing. Your teacher isn't standing there saying, oh, imagine that you do this and then that. I'm sure you can do that, but it's right in front of you. And finally, and this is an important thing if we're thinking about exploratoriums, the materials need to be cheap. It was really nice hearing about the mathematics in a suitcase thing, but paper snowflakes are surely the most important, the most widespread maths outreach thing in history. Billions of children, I'm sure it's billions. Okay, I've got no data, but so many kids are going to be doing that because it's something that you can take home. Not everybody has tangrams in their home, but they do have paper and scissors. Yeah, Lego. Lego likes to market itself as a learning tool, and Lego is really good. But paper snowflakes are better because you never run out of paper like you do run out of Lego. Mathematicians don't run out of lines, right? They don't run out of squares. Okay, if only more maths could be taught like this. This is the one problem with paper snowflakes. It doesn't teach you that much. Symmetry is nice, but yeah, if only more maths could be taught this way. So, here's what I think about now. So on the left here, you've got me, and I stand there. I'm in my bedroom. This is caught on a family camcorder. Yeah, sorry. You can play around with this thing. This is a nice mathematical shape. It corresponds to Zika virus. Zika virus has its proteins laid out in this way, and I can change the pattern, and this tells you how viruses evolve. So here's Zika virus's pattern, but Zika virus can evolve to have a pattern that's more like this, and this is what human papillomavirus looks like. That's the cancer-causing virus. And in the video, I explain why it's like that. I explain how to use it. I know it looks a bit confusing, but that's sort of the point. You start out and it's confusing, but the controls are simple. You get used to it. Okay, done.